is Matthew Sabo. I'm with Team SenseNC. We're from North Carolina State University in the United States. And today I'm going to talk to you about the technical and creative aspects of our sensor, the AccuFret. So the core molecular technology in our sensor is FRET, or fluorescence resonance energy transfer. For those of you who may not be familiar with that, that's a phenomenon when two fluorescent dyes are in close physical proximity. And by exciting one dye, you actually get a dual response from the other when one transfers energy to the other. So we thought we could use this to increase specificity by binding those both to Humira. So we use TNF-alpha and protein L. We bind those to the Fab region of Humira, and those are bound to your fluorophores, rhodamine and fluorescein. And what we do is we excite the sample, and we get one of two responses. If you have Humira, we get a response primarily from the rhodamine dye that was excited by the fluorescein. If you don't have Humira, the fluorescein simply fluoresces, and we can differentiate that signal from the one where you had Humira. So, like I said, we're using Humira as the facilitator for that FRET, but I want to show you really how we differentiate that. So our system is shown above, and on the far left, we have a standard UV cuvette sized for about a 70 microliter sample. And then we excite that, and like I said, we get one of two responses. So the top one would be in the absence of Humira. Your lower wavelength lights would be fluorescein, and you get a higher response from that. This is kind of exaggerated, but you get the point. If you have Humira, then fluorescein will then excite rhodamine, and you get this lower shifted response, which is shown in the green. We can then read that, filter it, do approximations with it, and we can give you a reading of how much Humira is in the sample. So how do we actually do this? This is a small, little complicated diagram of our electronics, but I really just want to focus on the sensing element of that. So we take a standard LED that emits around 470 nanometers, which is at the bottom of fluorescein's excitation range. We shine that into our sample, which contains your Humira, your dyes, your proteins, and then that gives us really two significant wavelengths out, which would be somewhere around 520, and then if you have Humira, you would get the rhodamine at about 575. We filter down the lower wavelengths of light. We filter those out. So we're really just reading the rhodamine wavelengths around 575 nanometers. We can read that with a photodiode, and then we can correlate that back to how much Humira is actually in your sample. So as far as creativity goes, I talked about the chemistry, but there's a lot of work that went into how do you actually make a functional device that a user wants to use and will use on a daily basis. So the number one thing that we heard from patients was that it needs to be compact and it needs to be portable. If you're a nurse, you don't want to take this around your hospital and have it be, all on a cart. You just want to be able to carry it around. So we have about 11 by 17 centimeter box, and all of the fluidics and all of the sensing device fits inside of that. In the center, you'll see our fluidics. It's just a single-use UV cuvette, standard for most hospitals, and we can provide that to patients in a single-use cartridge, preloaded with our reagents, and that would be in the future. Then all you do is add your sample. Currently, we only support serum. We're testing whole blood. We think based on the absorbance spectrums of whole blood and the wavelengths we're using that we can facilitate that, but we're just testing right now. And then once you want to run your sample, you just hit start, wait for your sample to finish, and you get this handy progress bar. And then once it's done, you get an easily readable output, both in a numeric format, say for a technical audience, and in a bar for maybe a less technical patient who just wants to see where they are on their regimen. So that's all I have for you today. I'd be happy to take any questions. Maybe take it easy on me. I'm an electrical engineer, so.
Thank you very much. Very interesting presentation. What I find very creative is the fact that you don't use solid support. In principle, it's solution-based, or at least the way I understood, and that is different from most of the other formats that I've seen. So it's very molecular. I like that a lot. On the other hand, it could be, or I can think of reasons why it might be problematic in the sense of interference. If I understand correctly, you use a protein that binds to the light chain of antibodies, or at least is not specific for adalimumab in general, while of course TNF alpha is. Do you know whether you get interference in your FC if you have people that have high concentrations of immunoglobulins or patients that are on IV treatment? Can you comment on that?
Right. So we chose the proteins, protein L and then TNF alpha. Protein L is bound to rhodamine. So we've provided that in large excess to TNF alpha, which is then bound to fluorescein. So what you would expect if you have just other antibodies that say don't bind to TNF alpha is that you won't get that response from rhodamine. You'll just see the fluorescein in your dye. If you get both of them, both bound to Humira, then you will see that rhodamine response from the protein L. So those were specifically binded that way so we could eliminate that kind of interference.
Okay. So what you actually say is we added in such a large excess that you don't see interference from patients that have high concentrations of immunoglobulins.
Correct.
Okay.
And we avoid those kind of absorption spectrums of rhodamine so that we don't see that response.
Yeah. Okay, clear. Thank you.
Thank you very much for your presentation. So I'd like to know, do you get any autofluorescence from serum or whole blood at 470 nanometers?
Yes, we do.
So how do you correct for that?
So when you have autofret, as we would call it in the serum, that is tend to be just a linear shift up and down. So we can correct for that by filtering out some of the lower wavelengths and looking at the peak of rhodamine. Now we have done some tests on the plate reader where we've compared the relative intensities of the fluorescein to the rhodamine, and that has given us maybe more significant results. And that's the more common way to measure with FRET in general, measuring the ratios of those intensities. And that does help eliminate some of that autofluorescence and things that you are mentioning.
Thank you for a very nice presentation and interesting to use FRET. One of my questions is you have a slightly more complicated chemistry and also all in solution. So you're preloading everything in your cartridge
That would be the ideal. Right now we do pipette chemistry and we pipette in the sample and then our reagents and then mix them with pipette. We're looking into how do we preload those cartridges, and we think based on as long as the proteins are stable enough, and maybe they have to be kept in a fridge or however.
my next question.
Then, we think based on what we've done, I mean, we brought them 3,000 miles across the ocean. We think we could probably ship them and have them stored, and they would be stable enough in a preloaded cartridge where you would just add the sample and that would rehydrate your solution.
So your sample will be stored properly in a fridge?
I think that would be expected.
Yeah.
I would be probably not the right person to talk to for that exactly, but I think that would be the most likely scenario.
But even with this chemistry, you managed to do the whole assay in the 5 minutes?
Correct. I was just taking samples up there about 5 minutes ago. I would say our average time to sample is less than 3 minutes.
Perfect. Thank you.
Hi. So you mentioned the usage of your device by patients.
Mm-hmm.
So how would you envision the sample handling?
So the sample handling could be done in a few ways. Ideally, this would be something like a finger prick, right? So we only require about 20 microliters of serum right now, and that is well within kind of finger prick range. So that's why we really want to experiment with whole blood, so that they could take a finger prick and then just add that to maybe the cuvette cartridge, that might be sized more appropriately to inserting something like that. We're still kind of investigating how that functionality would work, and having a user handle their own sample is tricky, but that would be how I would imagine them approaching the situation, would be the kind of familiar finger prick and then add your sample into the cartridge.